Hi everybody, welcome to this series of videos on modern optimization, and today we are going to learn another very exciting nature-inspired method to solve tough and challenging problems in computation and design, the so-called particle swarm optimization. Much like natural evolution, swarms are another natural inspiration to devise problem-solving methods. They often exist in nature. For example, we can witness swarms of birds, insects, fish, and there are even talks of swarms of flying robots for various uses. Sometimes these uses are as controversial as artificial intelligence-driven weapons. But why is it that swarms exist in nature? Well, they offer certain benefits. For example, a swarm can protect animals from the attacking predators. And that's because, first off, the groups are larger and louder than a single animal. Therefore, the swarms intimidate an approaching predator. Secondly, the predator can sometimes be confused as to which animal to concentrate on and hunt because there are too many animals to concentrate on simply. Also, a single animal may be easy to spot against a background, but when you have a swarm, the whole swarm looks like the background to a predator. Swarm is also useful in hunting for food. When many animals look for food together, they are more likely to find it. Finally, swarms may also allow quicker movement. For example, bike riders often move in groups because the front rider faces air resistance while the others ride behind it. After a while, the front rider swaps with another rider, and so overall, it is easier to move for the swarm. By the way, the links that appear on your screen, I've also put them in the description of the video below. So if you want to look into these interesting topics such as predator confusion effect, you can have a read of those papers. Because of all these benefits, swarms inspired a branch of problem-solving methods in computer science and artificial intelligence under the title of swarm intelligence. Wikipedia defines swarm intelligence as the collective behavior of decentralized and self-organized systems, be them natural or artificial. Decentralized means that there is no single controlling entity in the swarm, and yet the swarm behaves in a collective fashion. And that's just amazing. So the entire swarm collectively organizes itself to complete a certain task in a collaborative way. It is also called social learning, whereby the members of swarm learn from their society. And one of the seminal papers that introduced this topic is on your screens. It was published in 1993, and its link is also given below in the description. Swarm intelligence is seen in human behavior easily, and it has multiple components. The first component is inertia. That is, if we've been solving a problem in a certain way, we have a tendency to stick to our ways. Secondly, we also draw upon our past experience. We all get influenced by society as well and social behaviors, and change our ways to conform to the societal norms. We learn from what we hear about overall societal patterns, as well as what works in our locality, our neighborhood, or in our social circles. But despite all that, we also like to innovate to make new discoveries. So our overall swarm intelligence is a combination of all these factors, and it is down to each individual as to how much he or she goes in each of these many directions to form their approach to a problem. The particle swarm optimization is a meta-heuristic method inspired by swarm intelligence to solve problems in optimization. In many ways, it is similar to genetic algorithms as well, but its terminology is derived out of swarm intelligence and not from genetics. It is a popular method to solve difficult optimization problems. And like genetic algorithms, it also maintains a population, but instead of calling it a population, it is called a swarm here. And likewise, each member of the swarm is called a particle. While genetic algorithms use genetic operators like crossover and mutation to produce new solutions, PSO uses the notions of inertia, past experience, social influence, and innovation to produce new solutions or particles for subsequent iterations. I also gave a link to the pioneering paper on PSO in the link beneath this description. So now we discuss particle swarm optimization, but there is an acknowledgement first that some slides have been borrowed from this YouTube video. The link to it is in the description below. So suppose three friends are given the task to find a treasure in a terrain. Assume that some hints are scattered around the place to guide as to where the treasure is. Sometimes the hints are strong, and at other times the hints are weak. The three friends find these hints and convey the information around. So the three friends or the three explorers will use swarm intelligence to find the treasure. Remember, they will each remember what has worked from them so far by remembering their personal best location. This is the same as remembering your past experience. So they will also be influenced by their social circle. So everyone will be communicated or informed what is the best location found by the rest of the team. And they will also have some inertia. That is, they will also want to go a little in their own respective direction that they are currently moving in. By combining the knowledge of all these three components, they will each decide their next move. So essentially, these three pieces of information are shown with the help of these three arrows. The arrows represent three different solutions, but each individual or particle, as we call it in PSO, will combine them to decide where that particle moves next. Now, how do we combine these three solutions? Well, this explorer, or particle as we call it in PSO, was moving with some velocity in the current direction. So that velocity pushes it a bit in that current direction. But the particle is also influenced by its best past experience. So the past experience pushes it to also move in that direction. And finally, the social influence is represented by the team's overall best solution found so far. So the particle also tends to follow that direction somewhat. The net effect of all these influences is that our velocity changes from the former direction to this new direction. The particle's present location is the head point of this arrow, whereas the length of this final arrow means how fast this particle is headed now. And the arrow head shows the direction in which it is headed now. So the current direction has now been updated. Hence the particle has now a new location and a new velocity. And this way the search continues in the future iterations and the particle keeps moving on from point to point. But the question is how much to move in each direction. Notice we only move a little bit in each direction, but how much? Do we move a fixed amount in each direction, say 10 kilometers? But is that the best strategy? How do we know? Well, since we cannot know, a common approach is to move a random amount. So we generate a random fraction between 0 and 1, and we multiply this fraction with an upper limit or max. So if max equals 10 kilometers, we can move anywhere between 0 and 10 kilometers. While we may overshoot or undershoot, at least we have a flexibility of movement. But we can be even more flexible. Instead of using the same upper limit for each direction or each of the three pieces of information that we recombine, we can choose different upper limits. That way we can decide which information to prefer over others. So we can generate a random fraction for the current direction. Likewise, we can generate a random fraction in the direction of the personal best and the team's best. Because these are random fractions, sometimes we will go high in one direction and low in others, or vice versa. Hence, we shall explore different solutions. So if we had used fixed movements, a particle could only move a fixed path. However, using random fractions mean that we cannot certainly say where a particle will eventually land. Instead, it can end up anywhere at various places that are represented by these shaded regions on the slide. The exact path that a particle eventually takes depends on the exact sequence of the random numbers that the computer generates. This is why we run a PSO multiple times using different random seeds to get a representative set of results. Similarly, the entire team can follow any number of paths across these shaded spaces. While not all paths lead to the treasure, chances are that during some runs the PSO may reach the treasure. Hence, that is the benefit of using randomness or a stochastic process, when we do not know a fixed path to lead us to the final solution. But remember, randomness is not the only reason we get a good solution. Instead, we use knowledge about good solutions. First off, each particle has a present location that represents its present solution. So in this slide, each solution has two variables, x1 and x2, because we were exploring a two-dimensional map. However, at other times, our solution could have many variables, such as represented by the vector on the right side of the slide, because our problem may require that many variables. Moreover, we use random fractions to extract some part of the previous personal best and the team's best, or the global best, that is the best ever solution found by any member of the swarm. We use these solutions to generate sensible new solutions. Remember, I earlier said that each particle has a location, but it is also headed in a certain direction with a certain speed. If we go back to our physics classes from high school, the combination of speed and direction is called velocity. Now, when the PSO runs start, what should be the velocity of each particle? Well, what can we guess? So we just initialize the velocities of all the particles randomly. But of course, we put an upper limit to generate solutions within the sensible bounds. Otherwise, the particle will move too fast in a given direction. Now, in subsequent iterations, when we recombine with other information, we generate new velocity, and that in turn determines our next location. So we generate the new velocity by using the present velocity, the personal best, and the information about the global best. So to update the velocity, we look at the present velocity, that is the velocity of the particle I at present iteration d, the difference between the present location and the personal best, and the difference between the present location and the global best. Notice we will not simply add all of these three pieces of information on the slide, but instead we shall multiply each of these quantities with the random fractions that we mentioned earlier. So let us compute the velocity for each particle I for the next iteration d plus 1. To do that, we compute our first random fraction up to a certain maximum. So we generate a random number r1 and multiply it with the maximum called alpha. It is common to set alpha to 1. Likewise, we generate the next random fraction for the personal best, that is r2 times beta, where beta is commonly set to 2. And we generate r3 times gamma, where gamma is also set to 2. Finally, we multiply these fractions with the respective quantities, and add it all together to get the next velocity vi at iteration d plus 1. Notice the first part in this sum represents inertia because this is a part of the last velocity. The second part represents the past experience. It is also called the cognitive component. And the last part is the social component, that is a multiple of the difference from the global best. Now that we have got our next velocity, what is our next solution? Well, to get the next solution for this particular particle, we add the new velocity to the old location, and hence we get the new solution. Notice the values of the upper limits alpha, beta, and gamma determine what kind of algorithm we are using. If we use a high value of gamma, that means we are attaching a high weight to the global best already visited by the swarm. This will not allow the swarm to find new values. Instead, the swarm will converge to a previously found best value. Hence, PSO will only look to exploit the information that it already knows and make small adjustments around it through combinations of alpha and beta. The swarm with high values of gamma will converge quickly to a single solution. Likewise, if beta is high, the method attaches high importance to each particle's own previous best. So this means each particle will stay close to the best it has found individually so far and not explore away from it. Again, it is an exploitative method, though it will still allow some diversity in the swarm because each particle may have a different best. It should converge slower than the first method and continue to explore for better solutions a little longer. Finally, a high alpha means each particle is encouraged to go its own merry way, and in this case, the algorithm is highly exploratory and may take a long time to converge. So what is required is a balance. A popular strategy is to initially keep alpha a little high, but gradually bring it down in each iteration to allow the swarm to converge to a good solution. Now here is a pseudocode of the method. We initialize the so-called control parameters of PSO, that is alpha, beta, and gamma. We also provide the upper and lower bounds of the velocity so it never goes outside these bounds. We also set a limit on the iterations. Then we initialize the swarm, that is, we randomly generate the present locations and present velocity for each particle. Then we start iterating. And inside each iteration, we go over the entire swarm. That is, for each particle, we compute the objective function to grade each particle. Based on this grade, we decide whether we have reached the personal best for this particular particle, or we have discovered the team's best so far. And after we have done the above steps for all the particles in the swarm, we update the inertia, that is alpha. Remember, we said that we decrease alpha gradually in future iterations. And then we compute the next set of velocities and location for each particle. At this stage, we have computed one iteration of PSO. So we go back to the start of the while loop, which is in the third line of this slide, and repeat the process until we have run out of iterations. A little bit of advice. To set the maximum velocity, the normal practice is to set it up to 10% to between 10% to 20% of the search space. Now, what does that mean? Well, suppose our solutions are allowed to range between 0, 0 to 10, 10. Okay, we are considering a two-dimensional solutions here. Then the maximum velocity should be set at no more than 2, 2. So that is 20% in each dimension. Now, every time we update the velocity of each particle, We must check to see if we have exceeded the maximum velocity, and if so, we cap it. That is, we must check for each component of the velocity of each particle, and if any component exceeds the corresponding limit in Vmax, then we cap it. Similarly, we must ensure that each solution values are also within the bounds, and if they grow out of bounds, then we must clip them. So that completes this lecture. Feel free to try PSO, vary its parameters on your own favorite problem, and discover the behavior of how PSO works. Also read around. Go, for instance, on Google Scholar. Just search for the papers on the topics of particle swarm optimization. Pick out the most popular articles there and see what research is going on around the development of PSO as well as its applications. So do that, enjoy it, and I shall see you in the next video. Bye.